Yes, please. Go ahead. Handout answers. I actually solved a couple of them in class, so it might be in the videos. And if you've got a specific question, I can answer those questions on board. That's fine with me. Or you can come to my office. That's also fine. Okay? Okay, go ahead. Which one? Was it about corner maps? I don't know. Tamam. Tamam, ben alıyorum. Tamam. Okay, so anybody who remembers last time I promised you to do something that I don't remember it right now. Anybody who remembers? No? Anyway, I will remember it eventually, and later on I'll talk about it, okay? Maybe I'll talk about today without knowing what I talked about last time. So anyway, let's just roll. One of the things I think I mentioned about multiplexers, so maybe I can start my discussion today with multiplexers, hoping to cover what I promised to cover in the last minute of our last lecture. So maybe I can start with multiplexers, then go back to the design, right? Combinational circuit design. And also we covered in our last lecture the technology mapping, right? The NAND and NOR relationship with other AOI gates. Yeah, there are multiple ways of doing the optimization in the NAND level. And I just shown you a simple scheme where you replace AND with its equivalent, or with its equivalent and not with its equivalent, right? So there are, for example, for NAND technology, instead of using a NOT gate, right, you use its equivalent gate using NAND this way, right? Remember the NAND, a 2 input and 1 output gate. So you connect these 2 inputs with a wire, and then feed this input of NOT to both inputs of the NAND, okay, to get its equivalent functionality. Similarly, AND gate is pretty simple because NAND is just not AND, right? So you basically put a NAND and then followed by a NOT gate, but we know how to implement NOT, so we replace that NOT with a NAND. Okay, we just copied this one to here. And also, this didn't look like an AND, so let me just redraw it. Okay, so this is an OR gate. And remember the OR gates using De Morgan's law? Okay, it was, so if this is A, this is B, this is A plus B. If you look at the De Morgan's representation, A prime, B prime, prime, right? So what does that mean? That means A goes through a NAND, this one, B goes through another NAND, which is not, right? And then you NAND them together because this is actually a NAND, right? This is A prime, B prime, they are ANDed, and then you take the, negate the output, which is going to give you the NAND functionality. So therefore, this is equivalent to 2 NOT gates implemented using NAND, okay? And we put them through another NAND gate, just like this, to get the equivalent relationship. Okay? So we have seen, of course, a simple replacement with AOI gates. If you look at the AOI gates, you've got use AND, OR, and NOT gate. So whenever you see a NOT, you replace it with this. If you see an AND gate, you replace it with this. If you see an OR gate, you replace it with this. Okay? So you got an AND implementation. But that is, of course, not necessarily the optimal way of implementing a circuit using NAND gates only, because we have seen an example, remember in our last lecture, that if you, apply this strategy to your circuit, which was based on AOI gates, let's assume, then you will end up with 8 NAND gates, if I remember correctly. But then if you use Boolean expressions and put the Boolean expressions in this form, okay, maybe concatenation of that form, what I mean by that is the following. You got A, B, not, C, not. You barely see expressions like this. You instead see, this is it, De Morgan's, you got A plus B, right? N dot C prime, okay? I applied De Morgan's here. And I didn't stop there because I can also apply De Morgan's one more time, right? To get A plus B prime plus C prime.
So it should be A prime. A prime and B prime.
Yeah.
Oops. Yes. So, thank you. Okay? And then you can keep it this way, or you want to continue and write A, B prime plus C prime. Okay? Well, if you look at this expression, you will probably implement this. Oh, okay, this is a NAND gate, AB, that goes through a NAND, right? And then I have a NOT gate, which I know how to implement using NAND gate, right? And then an OR gate, which I know how to implement using NAND gates, okay? So you can implement this way, right? So if you just, let me just show you the logic diagram. So you got A, B, that goes a NAND, right? That one. And I have a C that goes another NAND, right? This is that one. And from now on, I've got a 2-input OR gate, right? Which I have to put it here, but I know how to deal with it using this transformation. So which means I have to put a NOT gate first here, another NOT gate here, okay, and then another NAND, right? Because this is OR gate implementation. One of the things that you realize that these are going to cancel each other out because these are 2 NOT gates, right? Complement of a you know, a Boolean variable is the Boolean variable itself, right? So they go away, okay? So what you get is your C and B, A and B goes through a NAND and they got negated. Their output will be negated, and then C goes through another NAND gate. So you use 3 NAND gates actually, okay? But if you look at this expression, this actually tells you that AB has to go through a NAND, right? And then has to go through with C, and you NAND together, okay? Okay, so you actually have to use extra NAND here to be able to implement the same functionality. Of course, this is a simple example. You could have more, you know, embedded version of this, such as maybe you can have a D here and then another NOT, right? So this is a NAND, this whole thing is another NAND, and this whole thing is another NAND, right?
Can I ask something?
Yes.
How AB prime, A prime plus B prime? And transform AB prime.
This is, I think, you know, redundant, right? Has to go away, I think. That's actually correct because this goes away, right? And this becomes equivalent. So what I was trying to show failed actually, because I was trying to show you with this simple example. It didn't work though, but I could have actually done the following. So let me just go back. Good that you catch that error, by the way. So let me just come back here and implement this instead, okay? In other words, I have, so I have A prime, C, right? C plus A prime, I'm sorry, B prime C, right? And the NOT. I just use distribution law to get here. And actually these parentheses are also redundant. Okay, I can actually now use A prime C dot B prime C dot. Is that correct? I just used De Morgan's law to here as well.
Yeah.
Okay, and finally I have what? One more De Morgan maybe. A plus C prime and B plus C prime. So you get used to using De Morgan's law actually. I applied it multiple times. Okay, so this is actually a product of some form, not exactly, but some form of product. of two sums. So I can actually use this to implement this functionality using NAND gates, because there are two ORs, and I know how to implement NOT gates. Okay? So instead of now I got A, and A goes through an OR gate with C prime, so I got this C prime. So let me just write it explicitly, then you will see the cancellations. So A, and this is C prime, so A goes through another NOT NAND gate, and then another again NAND gate, right? So this A goes through the NAND. Maybe I can use another color. Okay, so this is my NAND, right? I'm sorry, OR, not NAND, OR. This is my OR functionality. This is C prime, okay? And I ORed them together, and I got the result. And also I have B plus C prime. Okay, so I have B, C prime already implemented right here. So I have to put it through another OR gate, right? This is my OR gate, right? And this is my C prime, and this is my B. Okay? So this is C naught, and C naught and B goes through an OR gate, and I got the result. And finally, I have these two outputs going through an AND gate. Okay? So which means I have to put an AND and a NOT, right? To be able to implement the AND gate. Okay? So this is my AND, and this is my OR. Okay? Anyway, so now let's come back to the cancellations. Now, this actually, these two actually cancel each other out, okay? And this also cancel each other out. So instead of actually using these three NAND gates, I can get rid of them completely and connect C to the second input of the first NAND and the first input of the second NAND, okay? So I can actually just erase these NAND gates, okay? To help me reduce, of course, the number of gates, because that's the complexity that we're hitting. Okay, everybody agree with that? Two NANDs concatenate with each other produces nothing, you know, logically. So they can cancel each other out. Why? Because the complementation of a complementation of Boolean variable is Boolean variable itself. Okay. So if you look at it, there are no more simplifications to this circuit, right? Which means I use, question? No? So I use 1, 2, 3, 4, and 5 NAND gates to implement this functionality here, which is equivalent to this one, but instead I could have just used 2 NAND gates to implement the same functionality. Now my demo works. Okay? So what I was trying to show you is that you could, if you're given such a Boolean expression, if you've got the skills, you should be able to go from here to here so that you use minimum number of NAND gates. That is art, by the way. Okay? It's not an easy thing to do, because there is no systematic way of converting such a Boolean, complicated Boolean expression to something that is NAND friendly, let's say. Okay? Anyway, that was my point. That's first thing. The other thing I would like to talk about was two-level. You got a problem?
It's a little bit blurry. How can I focus it?
Balloon. Let's see.
Can be seen, understood, but it's...
How about this?
I think it's better.
Okay. So the other thing I would like to talk about, before I forgot, is the two-level optimization that I mentioned last time. Okay? What does it mean? It actually means that, if you remember, we use corner maps to produce simplified Boolean expressions, right? From SOP or POS forms or to truth table, okay? And we learn about that. However, we may have sometimes more than one output, okay? As a legitimate output. So you got the multiple inputs. This is your logic circuit. Okay, multiple inputs, And we know how to deal with if you got a single outputs, because you know how to draw the counter map. After drawing the counter map, you figure out the groups, right? And then you of course start with the biggest group possible inside the counter map by grouping ones together, and then you figure out the corresponding Boolean expressions. You stick to, of course, essential prime implicants, right? And you use as minimum number of essential prime implicants as possible. And then that will produce you a simplified Boolean expression. Okay? So we know how to deal with the first single outputs. However, if you got multiple outputs, you can apply the same logic to this one, this output, this output, that output, and that output. So you've got 4 different outputs, 4 different kernel maps. Okay? We didn't, I mean, I tried to talk about this in our last meeting, if you recall, that we need to do one more optimization. Okay, that is called 2-level optimization, because this expression, when you develop that expression, okay, in your kernel map, you didn't think about the other outputs as per se. So, which means some of the outputs of this circuit may have some common terms, okay, that you already use here. So in order to minimize the number of implementations that are common to all of these outputs, you implement them once, only once. But in order to do that, you have to figure out which common term that is shared by each one of these outputs, right? So that is actually very manual. There is no automatic implementation optimization, just like counter maps in this 2-level optimization. But if you look at the Boolean expressions of these outputs, you sometimes will clearly see some of the common terms are quite, there. By using some kernel map, or I'm sorry, De Morgan transformations, you should be able to see those common terms. And most of the time, you will not be dealing with long and very complex Boolean expressions. So I hope that you will see those common terms by just looking at the Boolean expressions. And I'll give you an example. For example, if you got 4 outputs, let's say, so let's suppose there are 4 outputs, A0, A1, A2, and A3, okay? And I've got 2 outputs here, so let's just assume there are 2 outputs, F1 and F2. F1 is given by A0, A1 prime, plus A3, A2, A0, okay? The second output is A2, A1, A3, plus A0 prime. If you look at these 2 Boolean expressions, you realize that each one of them is already simplified. You cannot simplify this anymore because it's there, right? There are some missing terms, as you can see, because they cancel each other out, so they do not appear in their Boolean expression. And for F2 as well, you cannot simplify this anymore. This is the simple form as far as it gets. Okay, next thing is, as I said before, this is good enough. This is the first stage. Okay? The second stage is to be able to figure out the common terms. Okay? So you look at these expressions carefully to see if there are any common terms. One of the things that I've realized is, let me just see if I already figured out some common term. Yeah, so A2, A3, right? A2, A3, and A2, A3 right here. Okay? So maybe I can just introduce T to be my common term, one of the common terms, to be A2, A3. Did you get the idea here? Instead of implementing A2, A3 twice, you just implement it once. And then use that for both, for F2 and F1. Okay? You just implement that once. The common term only once. A2 and A3. Okay, that's good. So let's just write this expression in terms of T, A0, A1 prime, plus A2, A3 is T, so this is T, A0. How about this one? This is T, A1, okay, plus A0 prime. Okay, so you see you got these common terms shared by 2 outputs, and you implement that T only once. Okay, the other term that might be useful is the A0, so you see this, maybe I can actually write this using the parentheses with A0, right? So maybe I can write this as A0, A1 prime, plus A2, A3. That's better, right? Because you see A2, A3 did appear, okay, as is inside the parentheses. And how about this? Can I write this using parentheses? Yes, of course, because this you can use distribution law, right? So if I write this as A0 prime plus A1, okay, A0 prime plus A1, and A0 prime plus A2, A3, right? A0 plus A2, A3. Actually, I did write this on purpose like this because I have to have this A2, A3, you know, to see the common term, okay? All right, so now this is T now, and this is T, okay? This is good. How about the rest? Well, one of the things that I realized is that, you see this is A0, A1 prime plus T, A0. T, sorry about that, yes. T, A0, okay? I'll use again distribution law to come back here. And remember, this, if you take the De Morgans of this expression, you get A0 prime plus A1, which is right here. Okay? So if you set another common term S to be A0, A1 prime, then this would be S. And what is this? This is going to be S prime. Okay, S prime, A0 prime plus T. Okay? And this would be, of course, S plus T A0. Okay? So this, now you got two common terms, T and S, and they both appear in F1 and F2. You see S and T, S prime and T. So which means, because using NOT gates in the implementation is pretty easy, right? It doesn't really sometimes even count as part of the complexity figure at the end of the day. So that's why S and S prime are like almost the same complexity. So therefore, you got S and T, they both appear in the expression, Boolean expression for F1, F2, and you implement them only once. Okay, just once. So therefore, you use less number of gates. Okay? So finally, if you draw the logic down, do we have more common terms? Unfortunately not. For example, if we had, this looks a little similar to each other, right? Used through a De Morgan relationship. However, unfortunately, this is not A0 prime. If this was A0 prime, then this would be TA0 prime, and this would be T0 A prime prime, right? So that would be another relationship that would be nice to see. However, it didn't work out, so no problem. We already figured out two common terms for these simple Boolean expressions. Finally, we draw the logic diagram, right? The logic diagram goes as like this. You got A0, A1, A2, A3. Okay, you first implement the common terms. What is the common term? First common term is A2, A3. You got A2, A3, okay? You put it through an NE8, okay? So to figure out which one, which common term? T. So I would suggest that you write the T on top of the wire so you can track it, okay? Second common term is S, which is A0, A1 prime, A0, A1 prime. So this is a prime, A0, A1 prime. Not you AND them to figure out the S. Okay, that's my S. So after the common terms are implemented, now you go back to F1 and F2. F1 is S plus T and A0. Okay, so T and A0 has to end together, right? So this is my T and 0. And I have S, OR, right? Let me just put an OR gate, and this is my final F1. Okay? How about the F2? F2 is S prime. S is right here. S prime and A0 prime plus T. Unfortunately, I have A0, but I don't have A0 prime, so I have to produce it somehow. Maybe I can just put it like this. A0, and I have T, right? So I have a T, OR them together to produce a 0 prime plus T. This term is right here. And I have S prime, right? So this is my S. Put a NOT gate, okay? And OR them together. Okay? Here we go. We got F2. All right? So this is my logic circuit right here. This is my logic circuit. Okay? So we designed what is inside of this logic circuit using two different levels of optimization. First optimization was based on Karnaugh maps. I didn't show it, of course. Okay, so this is the result of the first level, the Karnaugh map minimization. This is also Karnaugh map minimization. So we figure out these two terms, outputs, simplified outputs. Then we go through the second level optimization by figuring out two common terms, S and T. T was A2, A3, and S was A0, A1 prime. And then we write F1, F2 in terms of S and T, and of course the other inputs. Then we draw the logic diagram. Question?
What's the purpose of this? Does it reduce to delay time of logic circuit?
This basically reduces the complexity because you implement S and T only once. If you implement these two using AOI gates, you would use more gates. Okay? For example, T uses an AND gate. You got T in F1 and F2. If you didn't know each other, these two, F1 and F2, they don't care about each other. If they were to not care about each other, then they would implement this T twice. That means you use two AND gates. However, in my design, I only use one AND gate to produce T. Okay? And similarly for S. Okay, the S uses a NOT gate and an AND gate. Go ahead.
Can I ask?
Yes?
What if we use NAND gates instead of these gates? It would be more efficient?
Maybe yes. Yes. Are you talking about in terms of G, Gn, and V? Are you talking about in terms of these metrics, or are you talking about reality?
I'm talking about when we are using NAND gates, it became more efficient, right?
It becomes more efficient in reality. Not necessarily in terms of number of gate inputs, for example.
Okay, if we implement the NAND gates instead of these gates in real life, it's going to be more efficient, right?
In reality, yes. In reality. So what your friend is asking, if you were to design this circuit, same circuit, and actually, in fact, in reality, we never implement this circuit using AOI gates, okay? In reality, we use either NAND mapping, NAND technology, or NOR technology, okay? So if you were to use NAND technology, the most simple approach to that is to replace AND gate with its NAND equivalent, OR gate with its NAND equivalent, and NOT gate with its NAND equivalent, okay? And you will end up probably more number of gates than the number of gates you see here, okay? That's probably what you're going to end up. However, in reality, we can actually pack more than 10 NAND gates in place of a single AND. So it doesn't really matter if you use extra few NAND gates on top of the number of gates you see here, okay? That's the reason. Here, for example, I use 1, 2, 3, 4, 5, 6, 7, 8, 9 gates. And if I use NAND gate only, probably I will end up with 13, let's say. So the question is, which one is less complex? So in terms of G, Gn, V, probably this would be less complex in terms of these. But in reality, it's less complex to use the NAND implementation because, as I said before, 13 number of NAND gates is pretty simple to pack into a chip rather than putting all these, AND or, NOT gates into a chip. Okay? There are many improved implementation skills in terms of NAND technology. Yes?
Because of their size or their
size, and also people researched on it. In the transistor level, we've got a lot of research. Manufacturing is easier and less costly. Okay? You've got a question?
This should be anti.
Which one? This one? Yes, true. All right. right, guys. So this was the other thing I wanted to talk about today. The other talk is about, my concern was about multiplexers. Okay. Here's a multiplexer. That's the circuit diagram, or this is just like a simple geometric shape we usually use to represent a MUX, but you could see sometimes in Logisim and Multisim, for instance, different shapes. Okay, so for example, in Logisim I think they use the same shape, but in Multisim it's different. It's probably a rectangle or something. Okay, but the functionality is what is more important. So I got I0, I1, you got 0, 1, MUX, and you got a Y, and you got S. Okay, and we know that Y is S prime I0 and S I1. Why? Because if you look at the truth table, which I didn't draw last time, A0, A1, S, and Y, you would definitely see S0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. You have, so it's actually just like designing a Boolean circuit, by the way, because somebody has to give you the specification. Here's the specification. The specification says, if S is 0, please pass I0 to I. If specification says, again, it continues, if S is 1, then pass I1, not I0 this time. Okay, so just look at the truth table, how we are going to produce the output Y. If S is 0, okay, I know I0 must be in the output. So if I look at the I0, I see 0, then I have to put a 0 here. Okay, similarly here, S is 1. I look at I1, which is 0, then I put out 0. This is 0, this is 1, this is 1, this is 0, this is 1, this is 1. Okay? Say again?
Can you repeat?
Repeat? So I'm actually assuming that specification is given to us. Specification says if S is 0, please pass I0. If S is 1, pass I1. So I actually applied that rule to these three inputs. If S is 0, I pass I0. If S is 1, I pass I1. Okay? S is 0, I pass I0. S is 1, pass I1. You see one? Okay? All right, so, and from here, if you look at question.
What is the 0 and 1 inside the box?
Oh, 0 and 1 means that if S is 0, pass this input to output, and that one means if S is equals 1, then pass this input as the output. It's just a simpler notation, because it's a convention, right? You could pass, for example, I0 if S equals 1, if you write 1 here. Okay? Okay, so this expression, of course, is easy to derive. But if you apply your background on Karnaugh maps, right, theorems and postulates, you can, from the truth table, we know how to come up with this Boolean expression, right? Using the Karnaugh map. You just draw the Karnaugh map. Let me just do it for you. Okay. We got 0, 0, 0. I'm sorry. There's only one bit in this direction, so 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, right? So all you have to do, you have to, of course, you have to put I0, I1 here, and S is here, let's say. Okay, then putting this way, of course, you have to be really careful, because this basically says that S equals 0, I0 equals 0, I1 equals 0, okay? This cell. So let's just look at this cell. This cell says that I0 is 0, I1 is 1. So this is the column I'm looking for. And S is 1. So this is 1. Okay? And this one says I0 is 1, I1 is 0, and S equals 0. So this is probably this cell. And this one says I0 is 1, I1 is 1, and S equals 0. So this is 1. And I finally have 1, 1, 1, which is this one. Okay? You really have to make sure that there is a one-to-one relationship between the comma map and the truth table by placing these as I0, I1. I could have done I0 here and I1S here. It would not change anything as long as you are consistent between the truth table and the comma map. Okay? You have to have the same Boolean expression, exact same Boolean expression. If you could throw I0, I1, I'm sorry, I1 here, maybe I0 and S here, it would not change the results. Okay? Okay, finally, you got this Karnaugh map, right? And you know how to group them, right? So, do you have any 2x2 for size 4 group here?
No.
No, unfortunately. How about group 2? Yes? Yes. This one. This one. This one. Any more? No. 3. And I have covered everything, everywhere here. Every one of the ones, digital ones or logical ones, are covered. But I cannot choose all of the 3 because, for example, the one in here, for example, is already covered. These ones are already covered by the other prime duplicates. These are prime duplicates, by the way. But I cannot choose all the prime duplicates, you know, because one of them is redundant, which is this one. Okay? Because it covers ones that are already covered by another prime duplicate. All right? So all you have to do is choose the horizontal prime duplicates because they were the ones, they are essential. Okay? So this one and this one. What's the Boolean expression that corresponds to this one? Can you tell?
I0.
Yes?
S prime.
S prime, right. S prime I0. How about this one? Remember, you look at the row. Row is S equals 1, so it doesn't go away. So that is S. And column, you have I0 changing, so you actually wipe away I0. Okay, so I0 is gone, vanishes. You got I1 because it stays, so I1 is here. Okay, so therefore your final Boolean expression is y equals S prime I0 plus S I1 using Karnaugh maps. But that is identical to this expression. Okay? So actually prove that this is a right expression for the MUX. Okay? So you maybe you have already done for the section 1 in lab. Question? We don't have any problem? Okay, good. So one of the questions in the lab, for example, implement an AND gate or OR gate using a MUX, right? So for example, A dot B. This is my AND. And I'd like to write this AND in terms of, transform this expression into a form that looks like this. Because if this looks like this, then I can directly know how to, insert these inputs, or maybe the selection input, and get Y, which would be this output, right? That's the thing that you have to keep in mind. Whenever somebody says, oh, please implement it in NAND technology, or please use MUX case only, or maybe later on we will see encoders and decoders, implement this using encoder, implement this as decoder, you have to figure out a way, it's just like a puzzle, a way to use those combinational circuits to be able to implement a given Boolean expression. So the simple way to do that, you have to look at the Boolean expression of that combinational circuit, like MUX, for example, and the Boolean expression that you have in your hand, and make sure that they look alike, okay? That's the approach. For example, I can write this A dot B just like this, right? I can add BB prime here, because BB prime is just 0, and if I add 0 to that expression, it would not change the final logic, right? And I actually look at here, this one and that one, and I see that if I set S to B, this would be S prime, right? So therefore, my I1 would be B, and my I0 would be A. And now this exactly looks identical to this statement. Okay? So if I actually now get my logic, okay? If I put A0A here and A1B, and what's select input? Select input is B, and then I finally get A dot B here. Okay? question?
For kernel map, why we don't immediately we find 3 groups, right?
We figure out 3 groups, yes.
But we just use 2 groups.
2 groups, yes.
Why we don't use?
Because the one that I figured out, this column, right? So this one is another prime implicant. However, that ones in that prime implicant, this is a set of ones, right? So if I look at this one, this is already covered by this prime implicant. And this one is already covered by this prime implicant. So this is not an essential prime implicant. Okay? These red ones are essential prime implicants, and we always keep essential prime implicants. Okay? Only. Because this is just a redundant extra logic that would require you to use extra gates, and it will increase the complexity of the circuit.
If they are intersecting, so we don't use intersecting groups, right?
We don't use prime implicants that are covered by other prime implicants. Okay? This prime implicant is already covered by 2 other prime implicants. Okay? This prime implicant has got ones in it, but those ones are already covered by other prime implicants, so we don't need it. Okay? So the procedure is as follows. You figure out all prime implicants, then you take away the prime implicants that are not needed because other prime implicants already covered those ones. Okay?
What happens if we choose A for selected?
If you choose A, yeah, this probably will be same. It's not a unique mapping here, so you could just write A prime here. It would give you the same result. Okay? Okay. So, combinational circuits. MUX is a combinational circuit. Oh, let me also introduce you, since we're talking about MUXes, so let's continue our discussion to MUXes. Let me just also give you briefly an extension to that, right? The extension meaning that, why don't we just have 4 inputs rather than 2, correct? Why are we restricting ourselves to 2 inputs anyway? Because MUXes are general in their definition, meaning that if you got a MUX here, 1, 2, 3, 4, I0, I1, I2, and I3, right? And you got an output Y, and there is of course 2 select inputs because there are 4 inputs. Otherwise you could not select 2 other. So this is S0 and S1. Okay, so you got now 6 inputs to the circuit and 1 output. Okay? Question? You got a question?
That A or B?
Both A and B would work. Both would work because instead of adding B prime, you could add AA prime, right? And then make it look like this expression. You will realize that this could be either A or B. Okay? All right, so if you look at this expression, I'm not going to draw the truth table, of course, obviously, because of our space limitation. Rather, I would intuitively guess the Boolean expression, something just like this, right? So if you look at this expression, the reason that I wrote this down without the karma map was that I wanted to think about if S prime, because S prime is representing a negation operation, right? So if S equals 0, then S prime would be 1, so I'm actually selecting I0 here, right? So if I look at here and pursue the same logic, I would probably immediately say if I want I0 to appear at the output, then I would probably want S0 equals 1, S1 equals 1. I'm sorry, S equals 0, S1 equals 0. So which means if I multiply I0 with S0 prime and S1 prime, right? Sorry about that, this is not 0 of course. This should be 0, 0 so that I0 can pass here. In order for this to be true, then I have to put S0 prime, S1 prime here so that these both could be 1, 1, right? And if you got 1, 1 and multiply or end with I0, then I0 will remain. The rest of the other terms will vanish away or go away. So let me just show you that as well. So I1, for I1 to appear here, I want S0 to be 0, S1 to be 1. So maybe I should put S0 prime and S1. And then I2, S0, S1 prime, and I3, you may not see this expression, the far end corner, so maybe I can write it down in the second row, plus I2, S0, S1 prime, and I3, S0, S1. Look at this S0s, all these S0 and S1 crap. What do you see here? These are actually mean terms, right? This is a mean term, this is a mean term, this is a mean term, this is a mean term. And if you select a specific S0, S1 combination, only one of the mean terms will be 1, the rest will be 0. So if S0 is 0, S1 equals 0, that means this would also only be 1. This mean term is going to be 1. The rest will be 0. This is 0, this is 0, this is 0, which means all other terms are going to go away because they're all zeros. How about this? This is 1. So therefore, the output would be I0. Okay, question?
They go away because we chose S0 and S1 to be
0, 0, right, yes. I'm just going through all combinations of S0 and S1 to convince you that this is the right expression. If you look at S0 and S1, 1, in other words, 0, 1 combination, in that case, this would be 1. The rest would be 0, right? These are going to be zeros. So therefore, I1 will remain, and that would be your output. If S0 is 1 and S1 is 0, in other words, 1, 0 combination, then this would be 1. The rest of the combinations would be zeros. Therefore, I2 would be your output. And finally, S0 equals 1, S1 equals 1 would make this one 1, and the rest would be zeros. So therefore, I0, I1, and I2 goes away, only I3 remains, and that would be your output. Question? Yes, right. I mean, it doesn't have to be. You could have 3 inputs here, but you still have 2 bits to, to use, because it's more than 2. So therefore, why are we wasting the other input? Just put it there. Okay? Question?
Can we note S0 and S1 in MUX operator?
Say again?
Can we note S0 and S1 in MUX operator like that's 2, 2, 1, like the first MUX?
You mean this?
S0 and 1, the binary digits.
You mean this too? But these are select inputs. These are select inputs. Oh yes. Yes, 0, 0, 0, 1, 1, 0, 1, 1. Yes, for simplicity, yes, you can put that. Correct. Question?
What is the point of using MUXes instead of AND for other cases?
Again, the transistor level optimization.
Okay.
People produce these chips, and they are much more efficient than using, this functionality can implement the AI gates, apparently. If you use AI gates, your circuit will be more complex than their chip, because they have got all these transistor level optimization. They use, for example, 10 transistors. You would use probably 30 transistors. Okay? Again, from a logic perspective, it doesn't make sense. But from transistor level perspective, which is not subject matter of this class, by the way, it makes a lot of sense. Okay? What?
I was going to ask about the bottom left corner circuit.
This one?
Yes, the input AB, order of them, does that matter? Because if we put A to the I0, it doesn't match up.
So look, as long as you have an expression that just looks like this one, okay, and you are mapping I0 to A or B, doesn't matter, as long as you have the right expression that is mapped. As your friend said, for instance, he said that why are we just adding more BB prime? Let's add AA prime. Then set A to be your S, right? This is now S, not I0, right? This is S prime. Then this would be your I0, this would be your I1, right? According to this expression. I'm sorry. This is a I0 because this goes to S prime, right? This is I0, this is a I1. Okay? But you could have a different mapping, so you can change it. So there is no unique answer to that.
The order of the input doesn't matter.
It may happen that you can put a B here and A here, and all these mappings are right. Then you can use B here and A here.
It's still the same.
Look, let me just give you an example. So let's just choose A. Okay, here. And BA here and B here, right? Okay, so let's just use our expression. Okay, verify it if that's correct. This is I0, right? And S is A, so this is A prime, okay? A plus S is A and I1 B. I'm not just applying the formula. Okay, is this AB? Yes, this goes away. Correct. So let's just put B here and A here, see if you're right. Okay, if I select A0, okay, this is A0, I0 is B plus A and I1 is A. What do you get? Do you get AB? Do you get it? No. Then your answer is you cannot just randomly change the inputs orders. You have to map to here. Because in your mapping, you actually put I0 to a specific value here. A, not B. Right? Is that clear enough?
Yes, sir.
Okay. All right, so now this is my 4x1 MUX. Okay? 4x1 MUX. And this is my Boolean expression. Of course, you could go ahead and draw a truth table of 6 columns because there are 6 inputs and an output, but it would be really cumbersome to deal with the kernel map to give you this expression. It's always good that you look at the functionality and try to figure out the Boolean expression corresponding to that functionality. All right? Okay, so the other thing I'd like to talk about finally about the MUXes, that for example somebody is giving you a function, a random function, a Boolean function, just like this one. I mean, this is an exercise of that previously just talked about the team here. I talked about somebody actually has given you a function which is AB, a simple function though, and you try to use a MUX to implement it. So let's just, because now I have a bigger MUX, let's just make the function f to be also some complex function, okay? Such as f equals a b prime plus a c. Let's suppose that this is my function, 3-input function, okay? And I would like to implement this using a 4x1 MUX, okay? Again, the first approach was, you learned, just put this in a form that looks like this, right? That's good. I mean, that we can do. However, I would like to show you another method, okay? So the another method is based on the truth table. Okay, how many minutes do I have? 20 minutes? 2 lagging today. Okay, so this method is based on truth table, all right? So what I'm going to do is, I'm going to actually draw the truth table for f function because it's not too hard to do, just 3 inputs. Okay, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, I hope I have done it right. All right, so how do I do that? I have to first figure out it's an SOP form, maybe. It's the best practice here. So this I can write A, B prime, C plus C prime, right? And this I can write A, B plus B prime, and C. Why? Because C plus C prime is just 1, and B plus B prime is just 1. So I can do that. So here, this is going to A, B prime, C plus distribution law, A, B prime, C prime, plus A, B, C, plus A, B prime, C. Okay? They're all different, by the way, right? No? Oops. These are the same. Yes. Sorry about that. So this goes away because these are identical. Thank you very much. So let's just come back here. This corresponds to what? 1, 0, 0. This corresponds to 1, 1, 1. This corresponds to 1, 0, 1, right? In the truth table. So 1, 0, 0 is 1, 1, 1, 1 is 1, and 1, 0, 1 is 1. The rest is just 0. You know what? Why did I use this more complicated version? Because I want you to get used to SOPs and POS. That's why. Okay? I could instead just put A, B, and C corresponding values here and figure out the answer. Okay? That would be another possibility, but that's just straightforward. That's why I wanted to go through the SOP. All right, now let's look at this truth table. I would like to use this. Right? Okay, great. So let's see. If I look at this example, I figure out something very important. That if I use, because I'd like to do the mapping, right, between these inputs and the inputs in here. So I'm going to start with the mapping, the select inputs here, S0 and S1. So let's just say this is my S0 and this is my S1. In other words, I map S0 to A and S1 to B. All right? Would that be fair enough for everybody? Okay, if I look at the first two columns here, one of the things that I realized, when A and B, or S0 and S1 now, are zeros, okay, I see that F is always 0. It's always 0. It doesn't even happen, it doesn't even bind itself to C, okay, anymore, right? And AB not also, because they are 0 as well. So that means, if I draw this MUX here, 4 inputs, and this is my S0 and this is my S1, now they are connected to A and B, I see that when I set A to 0 and B equal to 0, this input is going to be selected, right? It's going to be copied to output. This is what this expression is telling me, which means that if this is copied here, and I see F is always 0 when they are 0, 0, that means I can actually put a 0 here. This would be automatically copied to the output. Okay? Can I do that? Yes, because this can only appear here if A equals 0 and B equals 0. Otherwise, we don't even look at it. Okay? Same logic. Let's just look at the second two rows here. When A equals 0 and B equals 1, I see that F is 0, 0 again. Okay? It doesn't depend on C, so I can actually put a 0 here. Why don't we just bother? Don't bother. Just put 0, because this is the place you only copy from the second input to the output if A equals 0 and B equals 1. Similar logic. 1, 0. When A equals 1 and B equals 0, I see that F is always 1. Always 1. So I can actually put a 1 here. And finally, A equals 1, B equals 1. What I see is F is 0, 1. But C is also 0, 0, 1, right? Then just put C here. Because C is copied to the output. All right? So therefore,
Can we write A instead of? Because it's also 1.
which one? Do you talk about third one? Yes, it's 1.
Can we write A?
A?
Yes.
Yes. No. Why? Because if you write A here, then that would yeah. I would not recommend it, but yes, you can write it. In theory, yes. Because the input has glitches all the time, right? There's a noise on the input. So therefore, if you connect it to A, even if you've got a noise, then that would also appear at the output. If you put 1, okay, if you've got a noise in the input, that's not going to be replicated to the output. That's why usually people prefer that one. But you could, in theory, yes. Okay? Question?
Why do you put 2 by 2 in the truth?
Say again.
Why do you put 2 by 2 in the truth table?
We didn't. We just looked at the truth table and see if I can use MUX, 4 by 1 MUX. The reason that we group these this way is because we have got 2 inputs, select inputs, and I connected one of them to A and the other to B. That's why. I could have done the mapping, instead of having AB, I could have done AC, CD, CA, whichever you like. However, then your grouping would be more complicated, right? I mean, instead of, for example, if I have AB instead of AB, let's just use AC. Okay, maybe that can answer your question. So in that case, I'm using S0 to A and S1 to BC, right? So which means I have to now look at if A equals 0, SC equals 0 case, then let me use another color. A equals 0, and C equals 0. Okay? So what does that mean? That means A equals 0, C equals 0, A equals 0, C equals 0. So there is no grouping now, right? So you look at this output and this output. It's 0, right? So you keep it 0. Okay? Similarly, A equals 0, C equals 1. So this one and that one. I see 0, 0, so that means this is 0. Again, if A equals 1 and C equals 0, then I have these two rows, and I see 1, 0.
B prime.
Okay? That is B prime, right? Because B is 0, 1. So if I put B prime here, it would be 1, 0. So this would be B prime, sorry. And finally, we got 1, 1, and 1, 1. I have 1, 1, so therefore, I'm going to put just 1 here. Okay, if it's AC. You see, you can put anything you like here. It's not about grouping in the truth table. We're trying to figure out when A and C gets the appropriate set of values, zeros and ones. Okay? Is that clear? So we are able to produce a complex Bloom function, any function actually, okay? As long as we've got a mapping between truth table and the function itself, now you know how to treat this problem in general, right? So my question about in the lab, right? I have AND implementation using a MUX. Just apply this rule. It will actually help you. Why? Because this is a general question, right? A general Boolean expression, and AND has a Boolean expression. Just put it here and 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 go through the same logic. Maybe in that case you would not use, of course, a bigger MUX. Maybe 2 by 1 MUX would be sufficient, more than sufficient. Okay? All right. Maybe 10 minutes. How many minutes do we have? Okay, digital circuit design, right? That's the most challenging part. Okay. So we would like to do combinational logic design, right? The logic design means that somebody gives you the specification, then you draw the truth table corresponding to that specification. Then we derive Boolean expressions using Cardo maps. Then we apply optimization for each output, okay? Just like we did previously for the two-level optimization. And we draw the logic diagram, maybe using AOI gates, but then preferably one of those technologies, NAND or NOR. And we finally verify that. That part is not the subject matter of this class, by the way, because you have to draw the truth logic diagram and then put it through a circuit simulator and then get some results, etc., etc. Maybe they look at the timing diagram, see if ones and zeros appear on the right spot. That's another whole world to deal with, by the way. I may have, by the way, a friend of mine who worked in, we used to work together, who worked in Broadcom right now in California. I may have a little get-together with the guy. He's going to talk about implementation aspects of different technologies, probably an emphasis on digital circuit design. Just to get, how to go from theory in school to practice in industry, okay? We may have such little get-together. I'll let you know maybe towards the, maybe in November, okay? In November, sometime in November. So you can have your own questions, ask the guy, how he has been through, difficulties, troubles he went through, and of course, anything related to digital logic, okay? He's really good hardware engineer, by the way. Okay, so let's see. Let me just give you an example, all right? So let me use my 15 minutes with a design example. This design example called BCD to XS3 code. Okay? BCD to XS3 code. Let me describe it first, because that's the English that most of our students are having trouble with, unfortunately. When I, for example, describe in a paragraph what the circuit is supposed to do, most of the students, they are capable of designing the circuit, by the way. They, don't get me wrong, they are like A-quality, A-level students. Unfortunately, they could not understand the paragraph that I wrote. that explains the definition. This, you know, disclose the details of the circuit. Unfortunately, they could not get that definition, description, and they couldn't do the the question, unfortunately. Okay, here is the definition. We add, so that's the definition. Add 3, binary 0011, by the way, to the BCD code words. Remember the BCD code words? We replace any decimal digit from 0 to 9 with its equivalent 4-digit binary number. Okay? So, for example, let me show you that. So this is A, B, C, D. These are my inputs. Of course, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and 0, 0, 1, 1. You got 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1. And of course, I don't stop here. Oh, sorry, that's the difference actually between the binary and the BCD. Okay? So I have got up to here is correct. There's no problem. However, this corresponds to the decimal number 0, 1, 2, 3, 4, 5, 6, and 7. But I've got 8 and 9. Okay? So if you go to 8, you would probably say, oh, it's 1, 0, 0, 0, right? Yes? Correct? Yes, 1, 0, 0, and 0. And if I go to 9, I got what? 1, 0, 0, 1. Okay. But how about if I go to 10?
1, 0, 1, 0.
It would be 1, 0, 1, 0, right? But that is your binary representation. It's not the BCD. In the BCD, remember, you got 1 and 0, 2 digits. This has got a representation 0, 0, 0, 0, and this has got a representation 0, 0, 0, 1. Right? So therefore, you use 5 bits to encode 1, 0. Okay? This is the BCD mapping that we talked about earlier. All right? So just keep that in mind. Okay? So the question is, of course, not that. The question is, this is actually asked in your homework, or maybe one of you guys raised a question about one of the homework questions. Maybe he's not here. And you have to keep in mind this mapping in order to answer the question in the homework. Here, this is a little different here. This actually says you have to add 3, the binary 3, to the BCD code words. Suppose these are the BCD digits or code words, let's say, and I would like to have 4 different outputs. Let's suppose I use A, E, F, G, and H. So if your input is 0, 0, 0, 0, specification says that add 3 to that input to get an output. Okay? 3 is this, 0, 0, 1, 1. If you add 0, 0, 0, 0 and 0, 0, 1, 1, what do you get? 0, 0, 1, 1, right? Okay, good. Because 0 plus 3 is actually 3 in the BCD domain. Okay, how about the second row? What do you get? 4. How about the third row? 5, right? 2 plus 3, 5. So this is 0, 1, 0, 1. How about the next one? 0, 1, 1, 0. 6. And the next one? 0, 1, 1, 1. All right. This is my 7. How about this? 1, 0, 0, 0, 8. Right? And you got 1, 0, 0, 1, which is 9. Right? Which actually you get by adding 6 to 3, okay, to get 9. Okay? Now, if you add 7 and 3, what do you get? You get 10. But I know that 10 is represented this way, right? So which means I have to have an extra output then, right? E, F, G. That would be a little complicated, so let's just change the question a little bit, okay? Let's just not worry about B, C, D, okay? Because it would actually increase the number of inputs to 5, okay? So I don't want it to happen right now. I want it to stay in 4 digits, okay? So let's just assume that it's just a binary adder, just a simple binary adder. So therefore, this would be 10. 7, 3 plus 3 makes it 10. So this is going to be something that you are familiar with. 1, 0, 1, 0. All right? I just changed the question just to make it more simple. Okay, finally, I'm sorry, not finally. You got 2 more. You got 1, 0, 1, 1 for 11 and 1, 1, 0, 0. Okay? 2 for the 12. 9 plus 3, 12. Okay? Everybody agree with that? Mapping? So all I did is just add to these digits, 0 to 9, okay, 3, to get these binary equivalent values. All right? Now, in the design example, if you look at the procedure, we first draw the truth table, and then we draw the column map for each one of them. Okay, and that's exactly what you're doing in the lab, by the way, right? The 8-segment display. It's exactly the same thing as this one. In the 8-segment display, you drove the truth table for each output, right? So we do the same thing here. So for E, I draw the truth table, not the truth table, the column map. Sorry about that, column map. Okay, and here is how it looks to me. 1, 1, 1. I got 1, 1 here, and another. Yeah, that's it. Okay. You see, from what happens to, so the question arises here because we have only 10 possibilities here, and whereas I have got 4 bits to represent a number, so that means there are 6 redundant, bit combinations that we don't even use. So therefore, those are going to be in here in the column map. Those are going to be some don't cares, okay? And those don't cares just are landing on these cells, okay? Because they don't appear, right? Because we don't care much about them. I mean, they are here, but they are not digits, okay? That's why we get rid of them. So these are the don't cares, okay? You can think of this as A, B, and C, D. Okay, I don't even put these zeros for simplicity, but these are 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. All right? So if you look at these don't cares, you will realize that an 2 by 8 big group here exists. So therefore, you got also these 2 to cover the other ones. Okay, so therefore, E is equal to A plus BD plus BC. All right, that's what it turns out. I'm doing it a little fast, but I want you to verify it. Okay, at home, just do it yourself, and that would actually give you more practice time. The second output, was this is a E. This is F. How about F? If I drew it correctly, please verify. Okay. In F, you got 1 here, 1 here, 1 here, another 1 here, and 1 here. Okay, you see 1, 2, 3, 4, 5 ones. I got 1, 2, 3, 4, 5 ones. And of course, don't cares. Those are don't cares. Okay. And I have to group them together. And how do I do this? Perhaps I can use the torus shape of the column map to get these, for example, 2, and maybe these 2. Okay? And that actually, unfortunately, stays, individual in there. But I can actually group it with this don't care, so that I get a better, simpler expression. So I group this 2. Okay? And that's the best I can, actually. And therefore, F is given by B prime D plus B prime C plus B C prime D prime. Okay? Just verify that, as I said, these are all subject to verification by yourself. And this is F. This is H. Let's just draw the H. H is actually very simple. You got 1, 1, and 1, and you got 1, 1 here. So these are 1, 1, 1, 1, 1, 5 ones, and those are the ones. And I've got don't cares here, similarly. So the best you can do, of course, group here and group here to cover all the ones, right? And that would give you the simplest expression possible, which is H equals D prime. And finally, you got G, which I'm not going to draw it, okay? It's like a homework to you. C prime, D prime, plus CD. Okay, that would be G. So you, after all, you got all these outputs and their Boolean expressions here after drawing corner map. Okay? One of the common questions from students is that, or do we have to draw the corner map for each output? Yes, you have to. Okay? That's the the cumbersome part of the of this class, unfortunately. And then after getting the Boolean expressions, you have to figure out the common terms, right? If there are any, of course. Okay? Just look at it. If there are any common terms, you can figure. We can look at it in our next meeting. Okay, together.